Nuclear physics. In Chinese, it's called 核子物理. So we'll be studying what's inside the nuclear. So let's just have a few terminology here. So this is the nucleus. N-U-C-L-E-U-S. Yeah, nucleus. Nucleus. Yeah. And inside the nucleus, so nucleus, inside the nucleus, you have proton. You can write it as P. You also have neutron. You can write it as N. So this one here in Chinese, this is 质子. And neutron in Chinese is 中子. Okay? And proton and neutron together are called nucleons. N-U-C-L-E-O-N-S. Okay? It's equal to protons plus, so protons plus neutrons. So this is called 核子. Right? Nucleon is called 核子. So, okay, so those are some basic terminology, and you know the electron, right? Electron is outside, so there's an electron outside, right? Outside of the nucleus. All right, so now I'm going to introduce some units. So U will be used. It's called Unified Atomic Mass Unit. Unified Atomic Mass Unit. So this is coming from for a C12, okay? So C has different isotope, right? So C is 6 proton, so the atomic number, so this one is designated as Z here, and then A there, right? So A is the atomic mass number. Atomic mass number. And this one here is Z is the atomic number. An atomic number is equal to the number of protons. So how many protons do you have? An atomic mass number, it's equal to, this one is equal to the number of protons plus number of neutrons, okay? It's your A. So in here, we have C, we have 6 protons. So inside of C, we'll have 1, 2, 3, 4, 5, 6. Let's say we have 6 neutrons. 1, 2, 3, 4, 5, 6. Okay? And they are plus. I mean, this is not the way they are arranged. I just draw them like this. Okay? 6 proton. And so this is a C, and I have 6 electrons, right? 1, 2, 3. Well, they have orbits and all that. They're orbital, right? 1, 2, 3, 4, 5, 6. Okay, so that's a C612, right? So this one here, C612 has, I'll change the color here. It has 12U. Okay, the mass is equal to an atom of C612, right? The mass is equal to 12U. All right. So 1U, so this is just a bunch of definitions. 1U is equal to 1.66054 times 10 to the negative 27 kilogram. Okay, and then for the mass of proton, So mass of a proton is equal to how many U? Equal to 1.0072766 U. Okay, so then this is going to be larger than that one, right? So that's equal to 1.67262 times 10 to the negative 27 kilogram. Okay, so that's the mass of proton, and this is 1 U. Okay, you can also do the same thing for the mass of neutron, which is slightly larger than proton, and that's equal to 1.008, right? So 7 instead of 8, right? So 665 U. So then that will be larger than that, and that will be 1.67493 times 10 to the negative 27. So that's 4, and this is 2. So larger than that, right? All right, you can also do the same thing for electron. I'm not going to write it here, okay? So this is getting kind of boring. So that's the basic stuff. And now we're going to continue. We're going to talk about binding energy. So what does that mean? So for C612, the constituents, this one here in Chinese means 构成分子. So what are needed to make up C612, right? Okay, so what do I have? So I have 6 proton, I have 6 neutron, and I have 6 electron, right? So that's the constituents of that. So now I can compute this one here, right? And then call this one here the mass of the constituents. Okay. And then I also have the mass of the C612 itself. So you are thinking that, am I crazy? Like, this is that. Okay, well, they are not, right? So this one here is going to be the mass of the carbon's atom, right? Okay. So the constituent is going to have more mass than this one. So this one is larger than that, according to scientists. And the difference is that this one is going to be equal to the mass of carbon atom plus the mass defect. Okay? Right. So there's a difference there, right? So the constituents, right? Okay. So there's a difference there, and I'm not going to go into the actual number here, and that difference is called mass defect, right? So what does that mean? It means that if I have 6 proton, and then I added the 6 neutron, okay, and then I have the 6 electron. If I want to actually break the C612, I need to add some energy into it, okay? And this energy is coming from this mass defect, because this is smaller than that. So I have this mass here, and this mass defect, I'm going to call that delta M, okay? So now if I'm writing the energy, I'm just going to say, well, this one requires adding some energy in there, and this energy's name is going to call binding energy. Okay, so if I put binding energy into a carbon 612, then I can break them apart. Okay, and just like if I have a carbon atom, I need to add some more mass defect, then I can actually get back to the mass of the constituents, which are the 6p, 6n, and 6e minus. All right, so then this binding energy, as you can see, is coming from this mass defect. I'm going to change the color here. This binding energy for the carbon 612. It's coming from this mass defect. So how are they related? So this binding energy, if you call it E binding like that, right? It's equal to the delta M, which is the mass defect, times the C squared. Okay, and this C is your speed of light. Okay, and this one is in kg, and this one is in meter per second, and this one's in joule. Okay, so if I have a carbon 612 and I add this amount of energy by using the mass defect times the 3 times 10 to the 8 square, then I get this binding energy. And if I put that amount of energy into this, and I can break them apart. Okay, right, so then I'm going to introduce a little bit more about mass. Okay, so mass, you have the total mass, which is also called relativistic mass. And what's relativistic mass? It means a mass moving at a speed, right? So close to C, okay? Close to 3 times 10 to the 8. So those are the same. And then you also have rest mass. Okay. So rest mass is equal to M0. And this is equal to MT, total mass. So MT and M0, it's defined as M0 times gamma. And this gamma is not the gamma of photon, right? The photon gamma photon. No, it's not. This gamma is the factor that defined as 1 divided by square root and 1 minus velocity of this mass, this rest mass. So your rest mass M0. And so V squared divided by C squared, right? So for example, if you have V equal to, say, C divided by 2, then you have 1 minus, so a quarter of C squared, right? So minus 1/4, right? So that's equal to 3/4, right? So then gamma in this case is equal to, we're going to flip that, right? It's going to be 4 divided by 3, right? So 3/4 is this one here, right? So V squared. So this is V squared, which is C squared over 2, C over 2, so C squared over 4, right? And C squared cancel out, so it's 1/4. So then 1 minus 4, yeah. So then that's equal to 3/4. So you flip that again, right? So this is your gamma. Gamma is equal to this. You flip that. I'm sorry, it's not gamma. It's whatever at the bottom, at the denominator, right? This one here is from here. The denominator portion is this one here, right? And then it's a square root, right? Square root. So we're going to flip that. Then it's become 4 divided by 3, right? So then this is equal to 2 divided by 1.732, right? Anyway, this is, larger than 1. So you can see the total mass is larger than the rest mass. Depends on what the speed you are moving at, right? So if you're moving at V equal to C, then this one here is going to be 1. So gamma will be infinity, right? So then your total mass will be infinity, right? Okay? So then this one here is roughly equal to, in this case, is equal to 2 divided by square root 3 M0, okay? If you are moving at C divided by 2, or which is equal to 1.5 times 10 to the 8 meter per second. So that's your total mass, and this is your rest mass. So if you have mass, okay, and you have this one here, M0, you are sitting there. So this is equal to the mass of an object at rest. Okay, so before we didn't think about this because we did not consider relativity. But now, if you are moving close to the speed of light, you have to consider this relativity. Okay, so then this m0 is called rest. It's called rest mass, right? But it's also called invariant mass. Invariant mass. Okay, so when your velocity equal to 0, you got this, and when you are moving at a v, now you got this mt, right? If v is very small, right, very small, then this will be close to 1. So then gamma will be just like 1. So there's no difference, right? So then this one, yeah. So when it's moving at a v close to c, then this one here will be larger than m0, right? And it will approach, and this mt can approach infinity when the v is approaching speed of light. Okay, so there's a little bit more definition of mass right here. Okay, I'm going to stop there. Okay, keep watching and keep learning more physics. Bye bye now.